Types of trees. Types of binary trees. Okay. Guys, before seeing types of binary tree, I want you guys to see this tree. I'll be back in just a minute. Hello guys, I'm back. Sorry. Okay. Okay, types of binary trees. First one is full binary tree. So what is full binary tree? The rule is every node has either 0 or 2 child. So there's a difference between binary tree and full binary tree. A binary tree can have 0 child, 1 child or 2 child. But in full binary tree, it can have only 0 or 2. If a tree, consider a tree is like this. If a tree is like this, at that time it is considered as a binary tree because the condition for a binary tree, each condition for a binary tree is satisfied. But when it comes to full binary tree, it is not a full binary tree because each and every node should have either 0 or 2 child nodes. So here for this we are having 2 child nodes good, for this we are having 2 child nodes good, for this we are having 0 good, for this we are having 0 good, for this we are having 0 good. But when it comes to this node, here we are having only 1 child node. So this is not considered. This violates the rule of full binary tree. That's why it is not considered as a full binary tree. What is the example of a full binary tree? This is the best example of a full binary tree. Or we can say, let me just say, add here also. I will not add here to show the differentiate between different types of binary tree. Okay. So guys, this is considered as a full binary tree, but this is not considered as a full binary tree. Why? Why? Because in full binary tree, every node should have either 0 or 1. If it is having a single child, that is not considered as a full binary tree. I hope you guys understood this one because it was little bit easy. Everything is little bit easy if you understood. So let's go to our next tab, which is complete binary tree. So in complete binary tree, what they say is all levels are completely filled. except leaf level or last level. Which is optionally except last level. So if our last level is not full at that time, nodes in last level are filled from left to right. So guys, let's see what this means. This means that if you are having a binary tree like this, okay, it says that all levels are completely filled. What does mean by all levels are completely filled? What is level? This one is one level, this one is one level, this one is one level, like this. This level, in this level, what are the nodes? This is a node. Let me just give names, okay. So in this level we are having one node, in this level we are having 2 3, in this 4 5 6 7. So it's saying that all levels are completely filled. All levels are completely filled. If all levels are completely filled, this is called a complete binary tree. But except leaf node, what does that case means? That case means so take this as an example. In this example, we are having one more level, right? This is our last level. So last level, if our last level is not filled, that time also it's okay. That time also it's acceptable as a complete binary tree. If this is the case, then it is not accepted. If this is the case, here last bit, this is last level, this is last but one level, this is last but one level. So here last but one level is also not completed, not filled. At that time this is not considered as a complete binary tree. It will be only considered as a binary tree, it will be complete binary tree if we are having incomplete field in last level. Okay, so this is stated by our first statement, first condition. What is our next condition? If we are having, if our last node does not contain few elements, and that at that time it should be filled from left to right. So here, but if we enter this level, see, from left this is filled, this is filled, this is filled. From here we are not having data, then this is fine. But if our tree is like this, at that time it is not considered as a binary tree, even though only the last level's elements are not filled. But here, according to a left to right condition, first left, right filled, okay, left, right, here only right is not filled. So we should expect that from here we should not have any elements. From here, if we are not having any elements, then that is also considered as a full binary tree, complete binary tree. Because see, in this example, left, yes, right, yes, left, yes, right we are not having. So when we are not having, we are expecting that from throughout this level we don't have anything. So throughout this level we don't have anything, right? At that time this condition is true. But when we encounter such situation here, we are expecting that throughout this level we should have no elements. But here we are having elements. At that time it violates the left to right rule. So that's why it is not considered as a complete binary tree. Everyone got it? So these are all levels. Everyone got it? If you are having any doubt, if any test cases arises in your brain, then ask it. Because as I said in questions, right, they will just say the words. We are providing complete binary tree, we are providing that, we are providing this, like that. They will not draw you and show you guys. Okay. If you are not asking anything, I'll consider that you have got the concept, and I'll move to next question. Not question, next type. Okay. Our next type is as you guys, which is perfect binary tree. Okay. So what are the rules for perfect binary tree? All internal nodes have two child. All internal nodes have two child. Here they are stating that compulsorily each and every internal node should have two childs. And we are having one more condition, that all leaves have same level. So basically I'll say what it means. Okay. Internal nodes. This is a root node. This is a simple example of a tree. Okay. Here what are the root nodes? 1, 2, 3, 4, 5, 6, 7. Here 2 and 3 are the internal nodes. What is a root node? Root node is 1. What is the leaf node? 4, 5, 6, 7 are the leaf node. First statement says all internal nodes should have compulsorily two child nodes. So here 2 is a root internal node which is having two child nodes. Good. 3 is an internal node which is having two child nodes. Good. So first condition satisfied. What is the next condition? Next condition says that all leaf node should be in the same level, which is, we already discussed what is level. This is level, this is one level, this is one level. So we are having root leaf node here, leaf node here, leaf node here, leaf node here. So all leaf nodes are in same level, right? Then that is an example of a perfect binary tree. Then which is not an example of perfect binary tree, we will see that. If we are having 1, 2, 4 here, and we will have 5 here, and we had 3 here. Here, first what I need is, just say me what are all the internal node present in this tree. I want you guys to write what are all the internal node present in this tree. Yes, very good, very good. Now 3 is not an internal node. Very good, guys. Here 2 is an internal node. So first let's check the first condition. All internal nodes should have two children. Here 2 is having two children. The first condition is satisfied. Let's go to the second condition. What is second condition? All leaf nodes should be in same level. Here what are the leaf node? 4, 5, 3 are the leaf node. 4, 5 are in level 3. Okay, let's consider this is as level 3, level 2, level 1. So 4 and 5 are in level 3. 3 is in level 2. Which is not right. According to this condition, each and every leaf node should be at the same level. But here the leaf node is not in the same level. That's why it is not a perfect binary tree. So guys, got the context? And here, if you understood this one thoroughly, then you would understand this note also. All perfect binary tree are complete binary tree and full binary tree. This node you should remember throughout the concept of tree. So all perfect binary trees are considered as complete tree and full tree, because what is the what is the statement? What is the condition for full binary tree? For full binary tree, the statement is either it should have 0 or 2 children. Every node should have 0 or 2 children. Here, every node is having 2 children, right? Integral node is having 2 children. So that's why this is also comes under, it covers the trees which comes under full binary tree. What is the rules for this one? All levels are completely filled. Here also all levels should be completely filled, as we are having 2 children. Completely filled means, what is the other way of saying it? All the internal nodes should have 2 children, right? That is the another way of saying it. Except leaf node, all the others should have 2 nodes, 2 child nodes. Because completely filled, a binary tree can have at most 2 child itself. If you want to fill uh, all the places, we have to fill 2 child nodes. So again, this is satisfied. And the next condition, which is last node should be in a same level. It's not same level. Last nodes in nodes in the last level should be filled from left to right. So here, as each and every internal node is having 2 child node, so it's same that we will not encounter this situation itself. We will not go to this condition equal itself. So it's basically saying all levels are completely filled and full stop. There is no exception or there is no optional. In complete binary tree, we are providing an optional, and for that optional, we are providing another condition. But here, it's like all levels are completely filled, full stop. Okay. So basically, if a tree is considered as a perfect binary tree, then that tree would be also a complete binary tree and also a full binary tree. This is a note. So till now, if everyone understood, then we will move to our next one, which is balanced binary tree. Okay, guys, you are learning new things. Full, complete, perfect, balanced. Okay, what is the rules for this balanced binary tree? This balanced binary tree is little bit confusing, guys. This is little bit complex. Everyone keep your attention straight. Okay, height of these trees is O of log n. I know no one got this statement, and let's just ignore this statement. That's it. We'll go to here, which is constraint. So if each node in our tree follows this constraint, that time that complete tree can be said as balanced tree. If any one node does not follow this constraint, at that time we will not call that tree as a balanced binary tree. So what is this constraint? The constraint is modulus of left subtree height minus right subtree height should be less than or is equals to 1. So what do you mean by subtree? What is left subtree? What is right subtree? We will see it using an example. Okay. So for now, just ignore the first line. We will just see the constraint. We will just see the condition. If each and every node in our tree satisfies this condition, then that is a balanced binary tree. 1, 2, 3, 4. So we will start with leaf node. We can start from any node. For simplicity, I am starting from leaf node. So modulus I have put. Okay. Left subtree. Left subtree means left of 4. Are we having any elements, or are we having any part of a tree? No. At that time we will consider it as 0. Right side also 0. 0 minus 0 is 0. Is this less than or is equals to 1? Yes, the condition is true. This node is satisfied. We will go to this node. Here also we don't have any left subtree. Here also we don't have any left subtree. Less than, it satisfies the condition. So next what we will do? We will go to this place. Okay. So left we are having a tree. Okay, we are having a part of a tree. So what is the size? What is the height? I am saying height. Height means we have to see from leaf. What is the height of this? From left side. From left side, what is the height? Height is 1 because this one. From right side, what is the height? We don't have any elements, that's why 0. So 1 minus 0. What is 1 minus 0? 1 minus 0 is 1. So 1 is less than or is equal to 1, the condition true. So we have completed this tree. We will go to here. Left side. What is the height of a left side? When we compare left side, what is the height? 1, 2. So 2. Minus what is the height at right side? 1. So 1. 2 minus 1, what? 1. Is this answer less than or is equal to 1? Yes. So this also satisfied. Each and every node in a tree satisfied by this condition, then that means it is a balanced binary tree. Let's take an example which is not a balanced binary tree, and then you will understand this concept even better. Suppose if this is a tree, guys, just guess at which node the condition gets unsatisfied. We will see each and every node, but just guess. Come on guys, come on. You have to guess. Shaili, you have to guess and say which node. Oh, you are saying this is a balanced binary tree. If you guys are saying this is a balanced binary tree, then say yes. Guys, I will wait for 1 more minute. I'm not sure you guys are not answering or you are trying it out yourself for each node. So for just calculation, I will give you 1 minute. After that, I will start. Okay, I think I will start. So we will see for root node. Okay, so we don't have anything, so 0 minus 0 will get 0, which is less than or is equal to 1. This is true. Basically, if each and every root node will be true. We will see here. What is the left side? Left side height is 1. Right side we are not having an element, 0. 1 minus 0, 1, which is less than or is equal to 1. This is also true. We will come here. Left side 1. Right side we are not having an element, 0. 1 minus 0, 1. 1 less than or is equal to 1. True. This is also correct. We will come here. What is the height of left side? So left side height is 1, 2. Left side height is 2. Minus what is the height at right side? Right side height is 0. So 2 minus 2, answer is 2. 2 less than or is equals to 1, the condition is false. So at this node, the condition becomes false. That's why this complete tree is not a binary tree. I have already said that if any one node is not satisfies the condition, then we can directly say that this is not a balanced tree. If we checked for this and it will come true, because 3 minus 2 is 1, 1 less than 1, it is true. But for this node, it is not true. So we will not consider it as a balanced binary tree. Guys, everyone understood this, or should I have to repeat it again? I have mentioned it earlier, it is a bit complex, that's why. Guys, if everyone understood that, just say yes, otherwise I will repeat it again. Yes. Guys, interaction, yes, please repeat. Okay. Hemant Agrawal, you joined in between. So in balanced binary tree, what it says is just forget the first condition. Okay, just come to the second condition. In second condition, it says that if modulus of left subtree and right subtree, the subtraction of left subtree and right subtree is, if it is less than 1 or less than or is equals to 1, then this is a balanced binary tree. So we will see for this node, what is the left subtree? We are not having anything at left, that's why that is 0. Right side also we are not having anything, that's why 0. 0 minus 0 is 0. 0 less than 1, condition true, that's why it is satisfied. We will come to this node. In this node, what is the left subtree? Height of left subtree means left side, how many elements are there? 1, 2. So height is 2. Right side we are not having anything, so 0. Right side of this particular node we are not having anything, that's why 0. So 2 minus 0 is 2. 2 less than or is equals to 1, this is not true, right? So this node fails the constraint. So if any node of a tree fails at the constraint, then this whole tree is not considered as a balanced tree. Whereas in this tree, each and every node, you can see here also, if for this node, what is the left height? 1, 2. 2. What is the right height? 1. So 2 minus 1 is 1. 1 is less than or is equals to 1. So like this, for each and every node in this binary tree, the condition is satisfied. That's why this is called as a balanced binary tree. If any node does not satisfy the condition, it is not a balanced binary tree. Got it, Hemant Verma? Yes, okay. So let's move to our last type, which is degenerate or pathological trees. This is not commonly used. Sorry, this is not the last one. Okay, we are having still two more types. So what does this say is every internal node has only one child node. So every internal node has one child node. And what's the one more condition? It's not a condition, but a point is it performance wise, it's the same as our linked list. So what does it say? We are having a root node and each and every internal node has single child. So let's take 2. For this we are having 3, here let's say 4, and 4 is having 5, like this. Suppose this is a tree. For what is the root node? Root node is 1. What is the leaf node? Leaf node is 5. So what are the internal nodes? 2, 3, 4. Each and every internal node should have only one child node. If that case is satisfied, then a tree is called as degenerated tree. So guys, this one was easy. Just the one condition, which is each and every internal node should have one child node. So we have seen a condition where we can have 0, 1, 2. We have seen a condition where we should have 0 or 2. Now this is a condition where they say each and every internal node should have compulsorily one child node. Okay. This one was simple. And okay, I'll cover in this one itself. So let's take one more example. 2, 3, 4, and one more thing, performance wise it is linked list. So guys, you can understand, right? Like a value is pointing to a node is pointing to one node, that node is pointing to another node, that node is pointing to another node, that node is pointing to another node. This is basically a linked list itself, because each and every, for a node, one more link part is null itself every time. So if it's null, let's remove it only. So at that time it is similar to linked list only. The performance wise, what will be the performance of linked list, what will be the time complexities, what will be the space complexities, everything will be same as linked list itself. Okay, this is also an example. Or if we took like this, 3, 4, this is also an example of degenerative, but this is also an example of our next type, which is our next type is left skew binary tree. So guys, I will not explain it more about it. It is just this. If it is inclined towards left side, we don't have anything at right side. That is called left skew. And you guys can guess what is our next one. Exactly. Right skew binary tree. And this particular tree is an example of that. I'll just skip it, okay? You guys know it. I'll just skip it. We'll go to the next part. We have completed with types of binary trees.